Good morning and welcome everyone. My name is, this talk is about a corner-based saliency model, and my name is Rueopas, and these are my co-authors. We are from Department of Computer Engineering, Chulalongkorn University. And before I begin on our work, I would like to give a rough definition of saliency. It actually refers to visual sciency. So when we look at a photo, notice that we don't look equally at every pixel like a computer. We probably look more around deers and spend less time on grasses and trees. We could simply define visual sciency as the amount of attention we spend on these pixels. And of course, this mechanism is accomplished by our visual system, and the whole process is not clearly understood yet. So the problem of this field is to know possible process of this behavior and to also simulate them on a computer. Normally we would describe the visual sciency by a sciency map. So it is a grayscale image that determines how interesting each pixel is. The wider area means it is more interesting as predicted by our model. How our brain does that is not very straightforward. Some factors are that determine visual sciency are internal goals. Some people personally like deer, so they just like to look at them. The second one is knowledge. Maybe deers are more meaningful than trees and grasses, which we consider them as a background. And the third one that our model focuses on features. Among the whole scene, the deers had a light brown color, but the whole scene is in the green tone, so the light brown color is more rare, and so it appears more interesting. The features don't limit only to color, it also has orientation, and in our work we use corner as our feature, which I will describe later. In the past, there are roughly three approaches to sciencey modeling. First one is custom definition. So we could try to come up with distant function of image passes and use it to compare with other passes to find the standout ones. The information theory approach can convert image passes to feature vector, and so they can determine the probability as a saliency. There are also many other approaches in the custom definition. The second approach, which is popular right now, is machine learning. So we just use a lot of input and output and let the network figure out how to compute the sciencey map. And the last approach that we are focused on is a biological inspired model. So it will try to base the computation on visual system. Ideally, the benefit of this approach is that it is more likely to cover edge cases like visual illusion, and another benefit is that the result may be able to guide the direction of research in other fields. The most well-known biological-based sciencey model is by E.T. and Koch. In sum, the input image is extracted into three features in parallel, and center surround difference mechanism is applied on each one. Then they are normalized and combined later into sciencey map. The rest of the talk will begin with why we chose corner as a feature and the algorithm in more detail, and our results. Why we use corner? Firstly, corner is a general shape description. Given a corner of a rectangle, by using Gabor filters, we could detect the change in their orientation, and we can assign them as a corner. So for a rectangle, we could get 4 corners, and for a curve, we can get intervals of corner along the circular path. In this way, we could represent most circular shape into circular dots. Even if a circle is by visual illusion, like in the last figure, we can still able to capture some circularity in the figure. And the second reason is that corner also contain important information, like the line ring. Most of us probably spend more time at beginning and ending of the line. So imagine a very long line. We would look first at the beginning and then quickly scanning through the end of it. So this implies that the corner information can be overlooked. So our algorithm will first simply extract 8 features and detect the change in orientation to extract corner features and use them as a Saliency map. But actually, the real eye fixation is more random, and we could not use only corner to predict it. So we could enlarge the corner points by blurring it with Gaussian, so in order to cover more of the fixation. And this is the overview of our algorithm. It consists of 3 stages. First, the input image are extracted into 6 channels, 2 for intensity in the above and 4 for colors. Then we extract 8 features, and the corner extraction stage in the red box is our core algorithm. We extract corner here, and then in the last stage, with some normalization and post-processing, we combine them in last stage and get a Saliency map. So in the first stage, for intensity,
the structure takes a long time, and its short-term benefit can be hard to realize.
First intensity map
So it requires a long-term
by
commitment at the policy level.
Obtained by average of RGB channels. And there are 2 kinds of receptive fields, so we have 2 kinds of intensity. First one is the on center, which we give the highest response when the light falls down at the center and there is no light in the surrounding. And we simulate this response by this formula. And there are also the opposite kind of cells, and we also compute it with this formula. For color channels, we first extract red, green, blue, and yellow, and then we compute color opponency, which simply is another color space for our visual system to yield 4 color maps, and we can compute it by these formulas. Now we have 6 channels, on, off, and intensity channel, and we extract 8 features. In the corner extraction stage, we extract 4 orientation using Gabor energy filter for 4 orientations. And for each channel, we simply multiply together pixel-wise to get a corner response, and then apply logarithm function to enhance the response in order to extract corner feature map. In the last stage, we do some post-processing by first subtract center from surrounding, and then divide the whole feature map by number of local maxima to give more weight on feature map with fewer peaks. And the result, we do experiment on Toronto dataset by Bruce, and it consists of 120 indoor and outdoor images. This is some of the results from the proposed model. One weakness is shown in the bottom row. The share has many corners, so our model simply assign a lot of corner as a Saliency. But in the rest, will look similar to the human fixation, which is shown in the center row, center column. In the dataset, every input image also comes with the bitmap of fixations as a ground truth collected from many people. The metric used for evaluation is area under ROC curve, and it is called AUC shuffle. More details on the metric can be found in the paper. In short, it determines the accuracy of the model by comparing computed Saliency map and the eye fixation bitmap. The model is compared with other 5 well-known models. Ours is shown in a red dashed line above. Vertical axis is AUC shuffle score, which determines the accuracy of the prediction. However, the accuracy is sensitive to post-processing by Gaussian blur. So we blur every Saliency map with varying Gaussian sigma as shown in the horizontal axis, and the trend is shown here. The graph shows that our model is competitive to other models. This is the mean and optimal values from previous trends. We also test our model on MIT Saliency benchmark, and from the 61 models, we rank 17 sorted by AUC shuffle score. The weakness of our model is that it works only on natural images. So if the input look like this, it will not perform well. Ours is in the last row, last figure. So it assigns a corner to a Saliency, and it cannot predict the one that is stand out the most. Another weakness of our model is it has no higher knowledge such as shape, faces, and object. In conclusion, our experimental results have shown that corner is a good choice for predicting Saliency, and there are also many researches on corner extraction in visual system. So it is possible that we have this mechanism. And finally, corner is a good shape descriptor. So the model can be further extended to cover more complex Saliency calculation based on shape. And that's all for my presentation. Thank you for your attention.
Yes, good job. Yeah, thank you. Yeah. Okay. Anyone have question? This is so interesting topic. Is it like you have question? Okay. If no question from the floor, it's my job to ask the question. Yes, so interesting. And what is you in your paper you say that there are many level of features, right? Low level, high level, and heuristic is a medium level of the features. Could you discuss what is the advantage or disadvantage of each level? Why you need to not use only low level, and what about the high level? High level should be better, but you say that you in the medium level, why you should use this level for your features?
So the most popular password is so the most well-known that is also biological based use 3 features, which is all low levels, and it is their intensity, color, and orientation. And so the medium, the next level is like a corner, but it has never been used before. Most people will focus on very high level like human faces because it gives a very good result, because people normally look at human face as usual, so they give a higher result.
Is that for the top down, right? Like you said that we have a top down and bottom up. Top down is mean like you have a goal. I would like to see the face on this picture. So can you your topic is for bottom up also, right?
Yes.
Mm.
Uh,
Okay.
the top down is like internal goal for each people. Like we are searching for a red object, so
Mhm.
we will focus on to look at red object.
Mm.
But the human face is also something not very obvious, but
Mhm.
it may be not our goal to look at people faces, but it is something we do every day, so
Mm.
it's like a one of high level features.
Mhm.
So it's maybe different thing of the top down.
Okay, one more question. Your topic is very interesting. And have you ever been think of the application of you will use this one?
Oh, I never done, but I've prepared some application from that's already existing, and so the application is first we can reduce the object detection time by limiting the processing only on the interesting area,
Mhm.
and also we can do video compression that we can discard all irrelevant or non-interesting
Mhm.
area, and also image retargeting, which is the resize of the image so it can fit well better on mobile device. And also there are commercial example like visual ad scan, so we can evaluate how customer first see the ads, so we can adjust it.
But I imagine of the auto driving, right? We have the auto robot, right? And can see who cross the road. You have the picture, right? At the road and the view, and have the people cross the road. If use your work to like predict that is the human or something like that.
Fine, human.
Yeah. Okay. Very good job. Thank you so much for Mr. Wirawit. Thank you.